All right, we're going to look at graphing linear functions. So we're going to take a look at graphing once again, but they're going to be in a slightly different form. All right, our vocab for today, our first one is function notation. And the whole thing with function notation, it's similar, or it's the same type of thing as writing y equals mx plus b. It's still a linear line, or in this case we're looking at linear lines. But instead of saying y, we're going to say f parenthesis x, and we say this as f of x. So we say this f of x equals mx plus b. Our next vocab word is family of functions. It's a group of functions, showing similar characteristics. And today, for a good bit of time, we're just going to be looking at linear functions. And the parent linear function we're going to be taking a look at is f of x equals x. Now, keep in mind, f of x is just a fancy way of saying y. So the parent linear function is y equals x, but we'll say it is f of x equals x. Next, we're going to evaluate the function for the given value x. So we're told f of x equals negative 3x plus 5 when x equals negative 2. So we're going to substitute in negative 2, and for every place we have an x. So we'll say f of negative 2 equals negative 3, open parentheses, so times negative 2, close parentheses, plus 5. So we simplify f of negative 2, negative 3 times negative 2 is positive 6 plus 5. So f of negative 2 equals 11. Now this f of negative 2, we don't do anything to that. In a way, you can think of that negative 2 being protected by the parentheses. So that f of whatever value will just remain that. And then we simplify using the order of operations to the right of the equal sign. Number 2, we have f of x equals 2.8x minus 5 when x equals 3. So once again, wherever we have an x value, we're going to substitute in the value 3. So we have f of 3 equals 2.8 times 3 minus 5. So f of 3 equals, so 2.8 times 3, 3 times 8 is 24, carry the 2, 3 times 2 is 6, plus 2 is 8, move the decimal over one time, so this equals 8.4 minus 5. So f of 3 equals, so here, minus 5. Keep in mind, when we subtract, we add up the place values. So 4, 3. So f of 3 equals 3.4. And that is our final notation. Alright, the next part we're going to look at is we're going to compare the graph of g of x with the graph f of x equals x. Now we talked about this function here is our parent linear function. This is our parent linear function. So in 3, we're told g of x equals x plus 3, and f of x equals x is already graphed here. So if we want to think about this, refer back to slope-intercept form, our slope is 1, the coefficient in front of x, so we think of as 1 over 1, and our y-intercept, since we're not adding or subtracting any value, here is 0. So that's that first line drawn here. Now g of x is also in slope-intercept form. So keep in mind it's in that y equals mx plus b, so y equals x plus 3. Once again, that function notation is taking place at that y value. Our slope here is 1, so think of it as 1 over 1, and our y-intercept is 3. So we go up 3 units, then up 1 over 1, or we can look at it as going down 1 to the left 1. Fully extend to the parameters of the graph, draw arrows at the end. So that is our function g of x equals x plus 3. So now we're going to compare that blue line, that g of x equals x plus 3, to f of x equals x. So if we take a look at the blue line compared to the black line, g of x is shifted, so we've shifted that entire line up by, and we can take a look at the origin, 1, 2, 3 units. Now 4, we also have g of x, but this time we have x minus 5. Our slope here is still 1 over 1, And our y-intercept, once again, that constant or number that's being added or subtracted from x, is negative 5. And f of x is already graphed here. So from the origin, we're going down 1, 2, 3, 4, 5. And our slope, rise 1, run 1. And we also can go the opposite direction. Connect with the straight line. Make sure to fully extend to the parameters of your graph. And now we're comparing the blue line to the black line. So g of x is shifted down, and it's shifted down 1, 2, 3, 4, 5 units. Now when we look for that shift down, I find it easiest to take a look at that origin. So at 0, 0, and see how many times we move that graph down. So here we have g of x equals x minus 5. Alright, now let's take a look at some more function notation. We're still going to be comparing the graph, the parent linear function graph of f of x equals x, and once again that's graphed in black on both of our graphs. So this first one we have g of x equals 2x. Now once again in function notation, that g of x is that y value. So our slope here is 2 over 1, and our y-intercept, the constant that's being added or subtracted here, is 0. So our y-intercept is at the origin. Our slope, we go up 2 to the right 1. So up to right 1. Or we also can go down 2 units, left 1. Connecting with the straight line, fully extending to the parameter of your graph. And now we're going to compare the green line, with the black line. So the graph of g of x, which is in green, make sure we label, and we're looking at it as more or less steep. Now in this case, it's going to be more steep. And you can think of that if you were going to ride a roller coaster down either the black line or the green line is more steep. You have a higher incline, a higher degree from that x-axis. So it's more steep than the original function f of x equals x. 6, we have n of x equals 1/4 x. Our slope here is 1/4, so we'll go up 1 unit to the right 4 units. And our y-intercept here is 0. So we have a y-intercept at 0, so that's the origin, up 1 unit over 1, 2, 3, 4. You might also go the reverse, so down 1 unit to the left, 1, 2, 3, 4. Connect those dots with a straight line, fully extending the parameters of your graph. And now we're comparing g of x, which is noted in purple, to f of x, noted as a black line. So the graph g of x is more or less steep. Once again, use that incline. If you were going down this, a roller coaster, going down a sled on a hill, which is more steep? Now the black line is more steep. So g of x, let's just say the graph of n of x is less steep than the original function f of x equals x. And so we can conclude when our slope is less than 1, and we'll be taking a look at this a little bit more, when the absolute value of our slope is less than 1, also greater than 0, we're going to have a less steep line. When the absolute value of our slope is greater than 1, we're going to have a more steep line than our parent function. Alright, hope you have a great night, and we'll be taking a look at this more tomorrow.